Can particles be in two places at once? Sounds like magic, but in the quantum world, it's actually possible. To understand how this works, we first need to look at two wave phenomena: diffraction and interference. Imagine a harbor protected by a breakwater. Waves crash against the barrier and break apart. But where there's a narrow passage for ships, something interesting happens. The wave passes through and then spreads out evenly in all directions. That's diffraction. Interference is what happens when at least two waves meet. When crest meets crest, the wave gets bigger. When a crest meets a trough, they cancel out. Amplification and cancellation. That's the whole trick. These phenomena don't happen only with water waves, but also in the case of light. They can also be linked in a certain way. Light passes through two slits. Two waves are created and they overlap. Where crests meet crests, we get reinforcement. Where crests meet troughs, we get cancellation. The dark bands indicate where the waves canceled each other out, while the bright bands show where the waves overlapped and reinforced one another. The result? A distinctive pattern on the wall. And that pattern leads us to one of the most mind-blowing experiments in quantum physics. And it's worth pointing out that striped pattern practically screams, this is the result of waves. Okay, but what does all this have to do with particles? This is where things get really interesting. We can perform this experiment not just with water or light, but by shooting individual electrons or photons. Things that, by common sense, should behave like tiny little balls. What do you think happens then? Will we still see a wave-like interference pattern? Here's the setup. We place a source of particles, photons, or electrons aimed in the same direction. One shot every 10 seconds. Remember, we're firing just one particle at a time. Enough time passes between emissions so they can't possibly influence each other. Along the way, we place a barrier with two slits, just like in the wave experiment. Ultimately, we line up rows of ultra-sensitive detectors that record every hit. We let the experiment run for 12 hours. When we check the results, the detectors show a pattern typical of waves, specifically an interference pattern. And remember, that only appears when at least two waves overlap. Yet here, we only fired something that should act like a tiny ball, and only one at a time, not two. Furthermore, the particles were emitted so slowly that they couldn't possibly influence each other, yet they interfere with themselves, as if they were in two places at once. To truly understand this, think of shooting bullets from a gun instead of photons. Obviously, a bullet could go through one hole or the other. On the wall, you just see two clear bands of bullet holes, nothing more. By common sense, particles, which we instinctively think of as little balls, should behave the same way. But the quantum world works completely differently, defying what seems like common sense. Now let's repeat the experiment, but this time with only one slit open. After 12 hours, the result is crystal clear. The interference pattern disappears. It's as if a single photon knows whether it has one slit or two to choose from and adjusts its behavior accordingly. In other words, the result of the experiment depends not only on the path the particle actually takes, but also on the paths it could have taken. Strange, even as one famous physicist said, spooky. How do we explain this? A single particle isn't a tiny little ball, it's a wave. So when it encounters two slits, that wave splits into two parts and starts interfering with itself. But then a question comes up. What exactly is waving here? Not matter itself. What's waving is the probability of finding the particle in a given place. This probability distribution changes over time. It shifts and forms regions where the chance of detecting the particle is higher and others where it's lower. But what happens if we try to spy on the photon and see which slit it really goes through? Let's set a trap for photons. We arrange the setup with both slits open and place a particle detector at one of them. Think of it like a hidden traffic cop. Its job is to notify us whenever a particle passes through. We start firing individual photons and wait 12 hours. When we check the results, the interference pattern is gone. Now it looks just like the gunshot pattern. We run the experiment again, but this time we switch the detector off. After a long wait, the interference pattern returns. Surprising, it sure looks like the particles know whether they're being observed or not. When observed, they act like particles, passing through one slit. When unobserved, they act like waves, as if they go through both slits simultaneously. How can we explain this? The key lies in the act of measurement. When we check which slit the particle goes through, the measurement forces the particle to appear at one specific point of its fuzzy probability cloud, that is, one slit. We never know exactly where the particle will show up. We can only calculate the chances of finding it in different places. This is why, when the detector at the slit was turned on, the photon could no longer behave like a ghost spread out everywhere at once. It became an ordinary localized particle passing through a single slit. Physicists say that its probability wave collapsed, restricting itself to one of the two possible paths. And as a result, diffraction and interference could no longer occur. With the detector turned off, no path information existed. The probability distribution spread out like a cloud again, allowing diffraction and interference to appear. So, can particles really be in two places at once? Quantum mechanics says yes and no. It all depends on whether someone is watching. Quantum particles show traits of both particles and waves simultaneously. Weird, but true.